are you doing?
Trying to balance it.
Roots are always where it intersects zero. Remember? If you would x minus 2 equals 0, you'd so where it intersects.
Okay, just to remind you, we got the post-test. That's today, tomorrow, or Wednesday in the testing center. Okay? That's a required element, and you can earn some bonus based on your improvement from the pretest. So try. Okay, you don't have to study, but think hard and try. Okay? Then exam 3 is this Thursday. So I think I got all this stuff up for you. Web work, review outline, and then quizzes. And of course, the most important thing is stuff that comes from this book. The test is going to reflect what comes from this book. Web work are problems from another system that I've chosen that are the best reflection of this, but this is really what the test is going to reflect exactly. Okay, so homework and worksheets, of course, goes without saying that those are helpful for studying. Okay, and then the final is a week from Thursday in that building, SCOB 210 at 7 o'clock. Any questions? Okay, so we left off, we were looking at the bicycle tire. And what was the situation we had when we left off Friday? What was the relationship of the tire valve and the pedal?
The tire valve was like cycling behind.
She said the tire valve was cycling behind, right?
Correct.
How far behind? 5/4. It's always an angle of 5/4 behind. So when we start, it's down clockwise from there, and it's behind. When theta gets to pi/2, it's at pi/4. It's behind. So the relationship of how could we write the angle that the tire valve has swept through in terms of the angle that the pedal swept through? So the tire valve angle so how can we write that as an expression of the pedal angle?
Theta minus.
Yeah, if the tire valve angle is always pi/4 behind, then we can write that expression there. So what we're talking about is the graph of sine of the tire valve angle, but our axis is going to be the pedal angle, right? So our independent quantity is going to be the pedal angle, but we want to graph the sine of the tire valve. And so that's how we do that, right there. So I'm repeating the pedal graph over here. The pedal graph is always blue, okay? So I'm just taking the pedal graph and I'm repeating it over here so we can see how they compare. So if we think about if the tire valve is always pi/4 behind, okay? If it's always behind, then how will that graph compare to the pedal graph?
Or it will be shifted pi/4 to right of number.
Okay, to the right. He's saying it's shifted to the right. Is that what will happen?
Mm-hmm.
And why does that make sense? It'll be shifted to the right.
Starts at
What's that?
Starts at the 3 o'clock position at a later time.
At a later angle.
Yeah.
So it'll actually start at the 3 o'clock position, not when the pedal angle is at 0, but when the pedal angle is where? At pi over 4. So after the pedal angle's got to pi over 4, then the tire valve will start its cycle. So the fact that it's to the right, does it make sense that it reflects that it's behind? Right? So if you think about increasing the angle from left to right, later angles are to the right. Later in terms of the angle, is to the right. So when you subtract from what we're getting at here is not about bicycles, okay? The bicycle example is just to help you understand why subtracting pi over 4 from the input, how does that affect the graph? It shifts it right. It shifts it right because that angle is behind the angle theta. And so if we were to imagine the angle increasing, if you're starting here and you're imagining the angle increasing, what comes first, the blue graph or the red graph? Blue comes first and then red follows. It's pi over 4 behind. It follows. Okay? It lags. That's why, so lagging would mean shifting right. Okay, so I want you to start with number 3, page 297. Today's material is on the exam, Wednesdays is not. Okay, so today is the last day for material on the exam.
And we do new material on Wednesday?
New material, but okay, so they asked about, for the pedal, what would cosine theta, what would that function represent? What is that function going to give us? So this is big time review. We all should get this. How do we describe a function? In terms of input and output. All functions, right, are about a process of a certain type of quantity entering into the process and then the process giving us something else. So what is the input if f of theta cosine theta is about this pedal angle? So what would the input be? He wants an angle first and foremost. Is it an angle? Input is an angle, okay. Okay, rotated clockwise or counterclockwise? Counterclockwise from the right side, or that we call the 3 o'clock position. Okay? In what unit? Angles are in radians. Radius lengths are distance, arc distance. Radius lengths are arc distance or distance above the horizontal vertical. Radians are angle. But the value is the same. Okay? But it could just as well be degrees. We just always practice using radians. But if we define it this way, theta could absolutely represent a number of degrees. That's perfectly valid. Okay, output. He wants horizontal distance. Agree? That's what cosine is. Horizontal distance of the pedal from the vertical, I'm just going to say it. I'm not going to write that out. So, horizontal distance of the pedal from the vertical diameter
in radius lengths.
measured in radius lengths. So normally that number would be like 0.7, right? Because it's going to be a fraction of a radius length away from the vertical diameter, or 0.1 or negative 0.5, right? Can we get a vertical distance of, or sorry, a horizontal distance of 1.3? Could we get a cosine equal to 1.3? Why not? What's that? Can you phone a friend? So can we get a cosine of 1.3?
No.
Yes, no. No, why not? The furthest that it gets to the right is 1 radius length when you start, or when you make it all the way around. You can't go 1.3 radius lengths because the radius is the furthest away you can get. All right? So in radius lengths, the furthest you can get is 1 away from the center of the circle. Okay, so we got the function, and so you all should have an image of what cosine is. It's what you drew, right, on top of page 298. Where does it start?
It starts at 1.
Midline, max, or min?
Max.
Starts at the max, goes to?
The midline.
Goes to the midline.
Into the
The
mid.
min is at pi. Back to the midline. So this is tracking horizontal distance from the vertical diameter. But it's tracking it on a vertical axis, you see? It's tracking horizontal distance on the circle, the vertical diameter. We've done that. We've already done that. Okay, tire valve angle. Compared to theta, or in terms of theta, what is our tire valve angle? Theta plus pi over 6. So we're going to graph. G is going to be cosine of
Theta plus
the angle of the tire valve. Is the angle ahead? Is the tire valve ahead or behind? How far ahead? Pi over 6, see? Right there. Plus pi over 6. It's pi over 6 ahead in angle. Easy, right? Ahead of the pedal by pi over 6. That's why we're adding pi over 6. So if it's ahead, then what will happen with the graph? Watch what happens when I turn this on. What are you going to see when I turn on the valve graph?
It's going to start.
You're going to already see a part of it, right?
Yeah.
Maybe. No, that's the wrong thing. Here we go. What happened? You see? Can you see that little piece of the graph? It's already started. It's ahead. So which way is it shifted?
Shift left.
Left.
So it won't start at the max.
It just starts over.
Well, it starts at the max, but it doesn't start at angle 0 at the max.
Yeah.
So this graph, when you add to the angle, you get what kind of shift?
That makes sense.
Shifting to the left. Does it make sense that when you add pi over 6, the graph will shift left because it's occurring first? It's occurring ahead of time, or ahead of angle. Ahead of angle. So as we go along here in angle, which the pedal or the tire valve happens first? Tire valve happens first. That's why it's left. It's happening first. And then, once we hit 0, then the pedal kicks in. Okay, any questions? Any questions? So, normally you might, you think plus pi over 6 shifts left. That's counterintuitive, but we're trying to help you see that it makes perfect sense that when you add to the angle, you shift it left. Why? Because starting earlier, you're starting that much ahead of time, or ahead of angle. So what I want you to do is flip to the next page is a blank page, 300. So, sketch. So make it the nicest graph you can there, and you want to sketch f of x equals cosine x, or sorry, sine x, sine x. And then I want you to sketch another function. I gotta think quick on my feet here. What is it that I want exactly? I want cosine x minus pi over 2. So use what you've learned through the bicycle example to sketch both of these. Yeah, no, actually, you don't sketch sine x. Just sketch cosine x minus pi over 2. Use what we just learned, okay? What would cosine x minus pi over 2? So you can start by sketching cosine. That's what I want you to do. That's what I meant to do. So start with cosine x. And from that, sketch cosine of x minus pi over 2. Cosine x should be a breeze. Here's cosine x.
It's starting at cosine x minus pi over 2 is because you start down here at 0, but then as you go up,
Pi over 2 is about 1 point. This is pi over 2.
basically. Because if you actually went all the way to 0, here it would start at 0.
You guys figure something out up here?
Yeah, it's sine x.
Okay, so we look at that cosine of x minus pi over 2. Well, how can we think about this? How can we think about cosine of x minus pi over 2 now?
What's that?
Anybody? To the right. Why to the right? It's after, right? The angle is going to be pi over 2 after. So if this one starts at 1 at 0, and this is lagging behind pi over 2, where is it going to be at 1?
0. Oh, wait. Pi over 2.
It's going to start later, or it's going to lag behind pi over 2. So it's going to be pi over 2, and then at pi, what will it be? 0? Yeah. Is that what you were thinking? No. Sorry. Okay. That was, I put a z in, okay? So when you get to Calc 3, we do everything in 3 dimensions. So I actually hit z, and that gave us a 3-dimensional graph. But we're back. Okay. All right. All right. So all I meant to do is change it to blue. So, okay. At 3 pi over 2, then, what will the value of this new function be? It's lagging behind, so it's going to be that. What about at 0? It's going to be this, right? This is minus pi over 2, so pi over 2 later, it'll be 0. What'd you say, Riley? Do you notice anything? Anybody notice anything? It does look exactly like the sine graph, okay? Sine graph starts at the midline, goes up to the max, back to the midline. This is exactly what the sine graph does. And in fact, it is. So let's, if I graph sine, I'm graphing both sine and cosine x minus pi over 2. So what's the point? The point is that sine and cosine are really the same function, just shifted left or right from one another. So cosine starts pi over 2 behind sine. So sine starts its cycle. Cosine does the same cycle, but if you started it at pi over 2. Ahead, sorry. Yeah, right. So cosine starts, no, it's behind. Cosine minus pi over 2 means cosine is behind, right? That was the whole point of this.
Yeah.
That the angle is pi over 2 before, less than. So it's following behind. Sine starts first, and then, so if I just graph cosine, let's see. I have to make cosine start pi over 2 later in order for them to be the same graph. Does that make sense? Here's cosine. If we want them to be the same graph, we got to make it start at a later angle. How much later? Pi over 2. So if we make it start at a later angle, pi over 2, then they're the same. Okay? So this is the idea that, just briefly, sine of x equals cosine of x minus pi over 2. So this is an equation of x, right? So is this. There's a big difference between both these types of equations, though. This one over here, when is it true? Yeah, so x has to be a certain value. What certain value? So x equals 4?
Yeah. No.
So what do? We subtract x and subtract 1, negative 4. Okay? So when x is negative 4, this is true. Now, for what values of x is this true? Here are your values of x. You're looking at it. So for what values of x is the first one true?
0.
Just 0. 0 is the only value of x that makes these two equal. What is this graph showing you? For all x's. This is true for every x. The graph sits on top, true for every x.
From negative infinity to
That's right. That's what that is. That special type of equation is called an identity. An identity is a special equation that's true for every value of the unknown, x. And you're seeing you're seeing that by the fact that the graphs sit on top of each other. No matter what x value you pick, the sine is the same as the cosine of x minus pi over 2. So when you hear the term identity, often trig is a very common place where we have identities. Identities are relationships of, as far as we know so far, we just know about sine and cosine. But relationships of sine and cosine that are true for all x. So what I want you to do is write me what cosine x equals as an identity of sine. So can you create an identity? What does cosine x equal in terms of the sine function? Create a new identity. So I'll go back and just graph cosine again. So sine is the pink one, cosine is the blue one. What would you? So we were asking, how would you have to transform sine to get cosine? What would you need to do to sine to get cosine? You'd need to make it start how? Ahead or behind or where it's currently starting? How much ahead? Yeah, so if you made it start ahead or back here, pi over 2, so let's try it. So now I've got cosine. Let's switch the sign to. Okay, we're back. X plus pi over 2. Another identity. That's another identity. Okay, here's still another one. This is the most common one, so this is good to talk about. If I have a circle, okay, and I want, say, the coordinates of that point. So this is any radius. I want the coordinates of that point in radius lengths. Everyone write it down. So what are the coordinates of that point measured in, not the units of the radius, but in radius lengths? What are the coordinates of that point in radius lengths? Everyone should be able to do that. What's the x-coordinate of that point? I didn't tell you what, I just gave you theta. So what's the x-coordinate of that point?
Theta.
Oh no, you better know this. What's the x-coordinate of a point?
No, cosine.
Theta can be anything. I'm not specifying an angle.
He wants like cosine.
Cosine of theta. I heard some of you were saying it, but there wasn't a air of confidence in the room. Okay? All right, so we got to know this. The x-coordinate is cosine theta. Does it matter what the radius is? No, because that output is in terms of radius length. So this estimate. Tell me, estimate the cosine theta for the angle that I've picked here. What would you estimate that to be? No, you wouldn't say radical 3 over 2. Say,
Pi over 6.
pi over 6 is an angle. Yeah, it'd be a decimal, right? So what would you estimate that cosine to be right there? .2. Is it 0.2?
Yeah. No.
What would you say? 0.8, 0.9, right? 0.8 or 0.9, somewhere around there. It's almost one radius length. Right there, the x-coordinate. Okay? Sine theta. Oh. What's the y-coordinate? Estimate sine theta for the angle that I've drawn. 0.4. Good estimate. 0.45. 0.3, something like that. So now that makes a triangle, right? This side is what? Cosine theta. This side is sine theta. This side is radius. And in radius lengths, what is the radius? 1. Because these are all these units are in radius lengths, right? So really that in radius lengths, that's 1. So this gives us another identity. Out of those 3 quantities, the blue quantities, what identity could you write? What's the relationship of those 3 sides of the triangle? Cosine theta plus sine theta equals 1. What do we think? Is that what it is? Pythagorean theorem. Thank you. Cosine squared. This is called the Pythagorean identity because it's based on the Pythagorean theorem of the triangle that you get when you set up that triangle based on the coordinates, x and y coordinates. As I rotate theta, I just have a different right triangle, but the Pythagorean theorem still holds no matter what angle you pick. So it's another identity. It's called the Pythagorean identity. True for all theta. What?
You always use 1. Like, because you're using radius lengths, not actual radius.
Yeah, so what is cosine measured in?
Radius.
Yeah, if that's that number of radius lengths, and that sine is in radius lengths, then that has to be 1, because we're measuring this whole triangle. It has to be consistent in radius lengths. Make sense?
Yeah.
What is that in the units of the radius? Right there. In the units of the radius. So if this circle was 80 miles, what distance is that right there?
Wait, if the radius was
If the radius was, say, 80 miles of this circle, how would we express that distance right there?
0.8 of 80.
We don't know it's 0.8, though. That was just an estimate. So what would it be exactly?
Would it be 80 cosine theta?
80 cosine theta. 80 cosine theta. Whatever the cosine is, times 80. So you had it, but you just were stuck on 0.8. Cosine theta is the exact. So and in miles, what's this distance right here? 80 sine theta. And in miles, what's that distance right there? 80. So it would still work. You'd have 80 cosine theta squared plus 80 sine squared of theta equals 80 squared. Okay? But the Pythagorean identity is when you measure in radius lengths, cosine squared plus sine squared equals 1.
And that'll give you the point. Sorry. That gives you a point on the circle.
Cosine theta sine theta is a point on the circle. That's right. Okay, so another outshoot of this is that anything we can write as a cosine function, we can also write as a sine function with a shift. Same thing, anything we can write as a sine function, we can write as a cosine function with a shift. Okay, so to test our understanding of that, so now when we write these, when we're modeling, and I got an example for you, so we want to model both ways. So there may be an obvious way, it's like, oh, this looks like sine because it starts at 0, 0 and goes up. So we're going to use sine. But now, knowing how they're related to one another with a shift, we could also write that function with cosine. So here's a quiz. See if we can do it. So model the situation. At high tide, shoreline is 20 yards from the stake on the beach. At low tide, shoreline is 58 yards from the stake. If high tide is at midnight and noon, write a function for distance of the shoreline from the stake in yards as a function of the time in hours. So this is putting together everything we've learned, all right, in the last 4 weeks. We're putting it all together. So let me point something out. You have to really think about this. High tide is at 20 yards. So let's write this. You really got to get this straight because it's easy to... High tide is at... Right, because the high tide means the shoreline would be getting closer to the stake, so it would be a shorter distance. Low tide, the shoreline recedes out towards the ocean, so the distance is greater. So when you're graphing this, we're talking about the max and min. Does the max occur at high tide or low tide? The max is occurring at low tide, and the min occurs at high tide. Does that make sense? Okay, so just make sure you don't the words high and low might mix you up, but high tide, it's the closest, so that's your minimum. Low tide, it's the furthest from the stake, so that's your maximum. Okay, go. Work on this.
So you're actually
I would suggest start by getting a rough sketch of the graph. Start by getting a rough sketch of the graph, and then from that rough sketch, build your function. So sketch the function roughly.
the min would just be somewhere between those two.
Just somewhere.
Not just somewhere. Directly in the middle. So you're back.
First sketch, rough, and then from the key parts of your sketch, then write the function.
You get it?
Remember, this high tide is your min. Low tide is your max of the function. Time. Okay, I'm going to come around. I want to see good sketches here. This is high tide, isn't it?
It's a good sign of the shit.
So we said
But it starts here. It doesn't. You have your view line at 39, right? Yeah. It starts at 20.
No, that's 60.
And midnight starts at 20.
78 divided by 2, right?
It could be a sine. It could be a sine graph with a shift of minus pi over 2.
okay, so 20 equals up. It's second. Yeah.
So then the amplitude goes from the midline. That's right.
What do you get your x-axis? What do you label your x-axis? Are you using 2 pi, or are you using like hours, like 24 hours?
Well, you can find your period because you have the period is.
T is the number of hours after midnight.
Oh, they want
T is the
hours.
number of hours after midnight, and at midnight, is it high tide or low tide? Which? High tide at midnight, is that the min or the max?
Or is it
The min.
2.9 hours?
That's the minimum.
2.9 hours. So.
So where is it going to start? Where's it going to start? 20, 58, somewhere in between? 20. And is the distance going to go up or down? Right. It's high tide, so the distance is the least, and then it starts to recede, so that distance will go up. Okay? So we're going to add this to your homework. Add this to your homework. I don't want to just show you, because there's a lot of good thinking that has to happen here. So we're going to make this part of your homework for Wednesday. What's that? It says high tide is at midnight, and then at noon again. So if it's so high tide will be the minimum, will be at midnight, and the next time it'll hit the minimum again will be at. So is that a full period?
12 hours.
Is that a full period? Is that a half period? Which is it?
I think
It's
but I guess from
high
one
tide,
high tide to the next high tide is a full period.
You'd have made a full cycle.
So from the min to the min
It's one full.
is it one full period? Yeah. I'll go ahead and put this text. I'll post it online with your homework, okay?